Hi, my name is Eliza Bosmans, and this is my lab for modern physics, and for pendulum motion. And the purpose of this lab was to observe the motion of a mass as it oscillates around the y-axis as it hangs from the spring. We analyzed the object's motion using tracker to extract position data, model the mass's motion using code, and compare the observed motion from the tracker to the predicted motion given by the glow script model written in Python. So the physics principles we use were Newton's second law, the momentum thing, and gravitation near the Earth's surface, spring force, net force, energy principle, and potential energy. The system is the mass, spring, and the Earth, and the surroundings are, I guess, nothing or everything else. Our main results are computational model adequately predicted the observed motion. Fundamental principles. The momentum principle relates the net interaction between system and surroundings to the observed motion of the system. Changes in momentum are related to the net force acting on the system. You can see that in these equations to the right here. The velocity update, which is the equation below it, uses initial velocity, change in time, and mass of the system, and net force acting on the system to determine the new final velocity of the system during a specified time interval. Position update, which is this equation right here, uses initial position and average velocity over a given time interval to calculate the system's final position. The other fundamental principles used: spring force, the force on the system due to a spring, which is given by this equation right here, and that is generally what was used. That makes that oscillating motion. And the spring always tends to pull in the direction to restore the relaxed length. So when the mass is hanging down and being pulled down, it wants to go up, and once the spring is compressed, it wants to be pushed back down. And then gravitational force near the surface of the Earth, force on the system due to gravity on the Earth, always points in the direction towards the center of the Earth. In this case, the y direction, where mass, m is mass in kilograms, g is the gravitational constant. Net force acting on the system is the vector sum of the forces, which is given by this equation here. These are the forces acting in opposite directions. Another fundamental principle was the energy principle. The change in energy of the system equals the work done on the system by the surroundings, plus the work due to heat exchange between the system and the surroundings. In this experiment, we assume that there's no work on the system due to the surroundings, and there's no heat exchange between the system and surroundings right here, because we define the system as Earth, spring, and mass. Change in energy of the system is the sum of all the changes of the energy in the system, and then these are the energies involved. Kinetic energy, given by this equation. Gravitational and potential energy near the surface of the Earth, given by this equation. This delta y can also be subbed as height. Spring potential energy, which is right here as well. So the details of the computational model. Written in Python, uses Newton's second law to calculate updating positions at each time step and use energy equations to find total energy of the system at each time step. Visualize the position energy data. Results of the model fit the observed data relatively well. This is part one. This is our gravitational constant, our spring constant, and the relaxed length. These are the equations for the relaxed. This is the length, the length of the spring, and this was the direction of the spring. The direction the spring force is pointing, which you can see because you divide the vector by its magnitude, and that gets you the unit vector. And that's the rest of this. And then this calculates out kinetic energy just using the equations that we had posted before. These equations right here are then typed into here to find these equations. And then this defines all the initial energies. This calculates the gravitational force given a certain vector, which is just mass times gravitation. Gravitation is negative because it's pointing down always. So it's a spring force, and then the two forces combine to find the net force. This is the updating the ball's velocity, which was also written in the previous slide, and the ball update position as well. Again, this updates the spring using this equation right here, this, and then this changes in energy, again calculated with those formulas before. This is the graph we end up getting, and as you can see, these end up canceling each other out. Move on. Model somewhat accurately predicted it. This is what it looks like. There's some good overlap. I think it has to do with my initial inputs of the system, but if it was calibrated correctly, it would have been on top of it. This one as well is different because my initial inputs were different. And then the additional questions. Is the energy principle satisfied? Yes, the total energy is 0 at each time step. The energies cancel each other out because there's no work done on the system and no heat transfer between system and surroundings. And then these are the two different estimates of the oscillation periods, and this is what we get. This slight difference affects spring constant calculation over on force. And that's the end. Thank you for listening.